Welcome to the next lesson in the topic of electric circuits, current. Today's key learning is match the circuit symbols to the names of components, outline what current is, apply the idea of flow of charge to the definition of current, calculate using the equation Q equals IT, and finally hypothesize how current plays a part in explaining sparks. We're going to take a look at what current actually is. We're going to focus on current through wires, as this is the circuits topic. What carries charge in a wire? It's the electron. And what is the charge on an electron? Pause the video now, have a think. When you think you know the answer, press play. The charge on an electron is -1. So, here's our electron. It carries a negative charge. And we're going to do something pretty similar to what we did in lesson 1. We're going to place it in between a pair of spheres. We've got a negatively charged sphere on the left-hand side and a positively charged sphere on the right-hand side. What happens when you put like charges together? They repel. So the electron should be repelled away from the negative sphere. Opposite charges attract. So we should find that the electron is attracted to the positive sphere. The overall combination of those two will end up in a movement of the electron to the right. Now let's build our model a little bit further. Instead of spheres, this time we have a pair of metal plates. The left plate is negatively charged and the right plate is positively charged. What will happen to the motion of the electron? Well, the same rules apply. It'll be repelled from the negative charge and it will be attracted to the positive charge. So the electron will move to the right. Let's take our model one step further. So here we have the two plates, but this time they're at either end of a tube. What's going to happen? Well, the same thing. The physics is the same. So the electron will move from the negative towards the positive. This is now our most basic model of what the inside of a wire looks like. Picture a wire as being an empty tube with electrons in it. You can already see how the cell will be able to push the electrons from the negative side towards the positive side. Each cell, each battery, has a negative terminal. And it has a positive terminal at the other side. They're kept negative and positive by means of chemical reactions that happen inside the cell. So, is this now a complete explanation of the idea of current? Well, it's part of one. So at the back of the cell, we've got the negative charge. It'll repel the electron and it'll be attracted towards the positive side. But this isn't quite right. There are a number of reasons that we can say that this isn't quite right. First of all, the electrons don't whip their way through the battery. That's not what happens. In addition to that as well, if it's the case that the cell is going to propel one electron around a circuit, then there will be a delay from the moment that you turn the switch on to when it gets to where it needs to be. So for example, if we were to power a torch, it's not the case that you press the switch and the light comes on a few seconds later. It's pretty instant. So this is clearly not quite right. Consider this instead. Here we have a bicycle chain. The bottom cog is the driving cog. If you take a look at the left-hand side of the cog, it is forcing the individual links of the chain away from it. If you take a look at the right-hand side of the cog, it's pulling those links towards it. The cog, just by turning, is able to move all of the links on the chain, whether it's in contact with them or not. This is how a battery works. If you imagine, the negative side of a battery is pushing the electrons away from it. The positive side of a battery is pulling the electrons towards it. And we end up with an image something like this. Not all materials are able to transfer electrons in such an easy way. Let's take a look at comparing what insulators and conductors look like before we can refine our model a little bit further. In an insulator, the electrons are fixed to their nuclei, nuclei being the plural of nucleus. So, in other words, the electrons are stuck on the atoms that they are with. However, in a metal, for example, the electrons are free to move past the other nuclei. This is a diagram of metallic bonding, and if you take a look there, you can see the electrons are able to move from atom to atom to atom. These are called delocalized electrons, and they're able to move from one end of a wire to another. The movement of electrons is called current. So now we can refine our model even further. Inside of the wire, the gold balls represent the nuclei. On the left we have the negative terminal, and on the right the wire leads to the positive terminal. The electrons are repelled from the negative terminal towards the positive terminal, resulting in an electron flow that moves from negative to positive. So, now it's time to see if you've understood what you've heard so far. What is your current understanding? Anyway, question 1. What is an electric current? Question 2. What is the difference between a conductor and an insulator? Make sure you use the word electrons in both of your answers. Pause the video now, have a go at these questions, and when you're ready to move on, press play. So, question 1. What is an electric current? An electric current is a flow of charge, which in a wire is carried by electrons. Question 2. What is the difference between a conductor and an insulator? In an insulator, the electrons cannot move through the material, as they are bound to their nuclei. However, in a conductor, the electrons are free to move between nuclei, allowing a charge to flow. What's the difference between this river and this river? Well, the one on the left is clearly flowing a lot quicker than the one on the right. The word current is often used to describe how quickly water is flowing. So we would say that the river on the left has a high current, and the river on the right has a low current. We're now going to take a look at current as a means of measuring the rate of flow of charge. And let's introduce you to today's main equation. Here's today's new equation. Q equals IT. Q represents charge. Why is it a Q and not a big C? Well, the Q comes from the original name for charge, which was quantity of electricity. If you think of it in this way, it makes perfect sense, because the amount of electricity that something could be perceived to hold, if something's got a lot of electricity, it might have a lot of charge associated with it. So that's where it comes from. Charge, quantity of electricity. I represents current. Now this comes from the French for current, which is intensité de courant, and that literally means the current intensity. And that makes sense too, because if you think of current as a flow of electrons, the current, or the number that represents the current, is actually telling you how intense that flow of electrons is. A bit like a river. So if there's a river flowing with high intensity, then you can imagine that it will be flowing very fast. A high intensity current is where the electrons are flowing fast. T represents time. So your equation then is Q equals IT, charge is equal to current times time. So let's take a look at that equation in a little bit more detail and add the units in. So, charge is equal to current times time, or Q equals IT. The units are as follows. Charge has a new unit, the coulomb, capital C. Current has the unit of an amp or an ampere, which is a capital A, and time is measured in seconds, which is a lowercase s. Now previously we've talked about the fact that the charge carriers in a wire are electrons. So why can't we just talk about charge as being a number of electrons? Okay, so why coulombs and not electrons? Well, 1 amp, which is a typical amount of current that flows through a wire that we can use in school or in experiments or in the house, is equal to 1 coulomb every second. Now electrons are tiny and they have a really small amount of charge. And in fact, there are 6.25 times 10 to the 18 electrons in 1 coulomb. So 1 amp is 6.25 times 10 to the 18 electrons per second, or 6.25 billion electrons per second. That's an unimaginable amount of electrons and a very big number for us to be working with. So you'll be glad to know that we use the coulomb as a measure of charge. So we're going to work through a couple of worked examples. What I have here on the right hand side of the page is a checklist. The checklist is going to give you a prompt for everything that I want you to do in order to answer these questions as fully as possible to gain the maximum number of marks in examinations. Okay, so let's go through this in order. So number one, list the quantities that you know from the question. So let's take a look at the question. How much charge is produced when a 5 amp current passes through for 20 seconds? Well, we've got the current, so I would write I equals 5 amps. And I would say that we've got the time. Time is equal to 20 seconds. Okay, so we can tick that one off straight away. Convert any units. Well, we measure current in amps and we measure time in seconds according to the standard equation. So we don't need to worry about that one. So we can just tick that one to say that we've done it. Then write out the equation that you will use. Now, what I would always do is write out your equation so it's nice and spaced out. You'll see why in just a second. So Q is equal to I times T. Done. Next, substitute the quantities into the equation. Okay, so we have here, we've got the current. So we're going to put the current here. So substitute just means to write the numbers into the equation instead of the symbols. So current is 5 and time is 20 seconds. So there we go. And you get a mark for that in the examination. So even if you mess up the calculation, as long as you have that, then you at least get some marks in your exam. Though it's really important that you write it out. Rearrange the equation if needed to. Well, we don't need to. We've got Q equals I times T. We're looking for Q, so we're absolutely fine with that. So we don't need to rearrange the equation on this occasion. And then calculate your answer. Now, it's very tempting in order to get the question done quickly to just do this in your head. And you can do this in your head, of course you can. But I would strongly recommend that you don't, because under examination conditions, your brain does funny things. So I would strongly recommend that you use your calculator at all stages, no matter how easy the equation is. Okay, so that's 5 times 20, which is equal to 100. So there's your calculation, and then make sure you include the units. So charge is measured in coulomb, so therefore we will say 100 coulombs, and that will be your final answer. So you get a mark for the substitution, a mark for the right answer, and a mark for the units, which would typically be a 3-mark question. And we're done. Let's take a look at another one. So this time, what is the current when a charge of 120 coulombs passes through for 1 minute? Okay, so let's write down what we know already. So we've been given the charge. So list the quantities that you know. We've been given the charge. So Q is equal to 120. And we've been given the time, which is equal to 1 minute. There we go. Right. Convert any units. Well, first off, the charge is in coulombs, so we're fine with that. But time, do we measure time in minutes? No, we measure it in seconds. So we do that conversion nice and early. So the time is equal to 60 seconds. And there we go, we've converted the units. Then write out the equation that you're going to use. Same as above, make sure there are there's lots of space, lots of room. So Q equals I times T. Okay, so there we go, written that out. Substitute the quantities into the equation. Well, Q is 120. So 120 equals... we don't know I yet. We're being asked for I, so we'll leave that as I. Multiplied by the time, which we've done the conversion from minutes to seconds, is 60 seconds. Okay? Then rearrange the equation if you need to, which we do need to on this occasion. Okay, so if 120 is equal to I times 60, then I is equal to 120 divided by 60. Which, again, you may be tempted to just simply do that in your head. That's absolutely fine for now, but in an exam, don't do it. Do not do it. 120 divided by 60 gives you 2. So this is 2. So done our calculation. Final step is to make sure that you include the units. And the unit for current is the ampere. So there we go. So 2 amps. And that is our final answer. Calculation time! So, we're going to have some practice using this equation. Here are some questions. Make sure that you answer the questions as fully as possible using the technique that I've just shown you. Pause the video now. When you're ready to check your answers, press play. Let's take a look at those answers then. Question 1. The current in a wire is 1.5 amps. Calculate the charge that passes through the wire in 12 seconds. Should be 18 coulombs. In 17 minutes, should be 1,530 coulombs. Question 2. Calculate the average current in a wire if a charge of 270 coulombs passes in 40 seconds. You should have 6.75 amps. And in 2 hours and 40 minutes, that rounds off to 0.03 amps. The current running through a toy train is 180 milliamps. How long would it need to be left on for 4.5 coulombs to pass through a certain point in the circuit? Here it would take 25 seconds for that to happen. If your answers don't match any of the ones that are in front of you, then what I'm going to do is I'm going to show you my working. It's going to be over the next 3 slides, so pause it at any point that you need to check your answers. If you have answered everything correctly, then we should be resuming the original presentation within the next few seconds. So now we're going to take a look at an experimental setup to see how we would measure the current. Before we do that, it would be useful for you to have a go at the following task. Match the following circuit symbols to the correct component names. Pause now, have a go at this task, and when you're ready to find out if you're right, press play. So let's see if you're right. So, the top symbol there, that is a lamp. It's also perfectly acceptable to say that that is a bulb. The next one is a battery. Third one is a variable resistor. And finally, we have an ammeter at the bottom. Make sure that you've checked your answers, correct them if necessary. Now we're going to take a look at an experiment where we are going to measure the current. This is the circuit I'm going to be using to measure current. As you can see, I'll need a battery. I'm going to use a bulb. In order to change the current, I'm going to use a variable resistor, and I'll use an ammeter to measure the current. changing the variable resistor, you can see that there is a change to the ammeter reading and the bulb brightness. Note what happens to the current and the brightness of the bulb as I adjust the variable resistor. Now, think back to year 8. Is the current the only thing that's changing in this experiment? What else might be changing? Next lesson, we'll be taking a look at potential difference and how it's related to current. You'll find out that in order to describe what's happening to the bulb, you need to know about both the current and the potential difference. So here's your final task. I'd like you to revisit the sparks question. You should have already written something in the field section on why you think we get sparks, but also you should be able to add something from today's lesson into the current section. So make sure that you do that. We'll be having a look at the potential difference in the next lesson. Thanks for watching. That's the end of the lesson.